welcome to lecture number 7 of this master course, Renewables and Electricity Markets. Today we are going to talk about impacts of renewables on electricity markets. This is the last lecture of the course from power system and market perspective, right? So from the next lecture, we are going to talk about, so from stakeholders, individual market participants' perspective, specifically about their offering strategy, how they can optimally place bids in different markets, right? So, but today is the last lecture from system perspective. And that's why the deadline of your assignment, number 1, is next week. Good, so let's talk about impacts of renewables and electricity markets. And today, the specific learning objectives of the lecture today is, hopefully after today, you will have a good idea to be able to explain how the growing share of renewables affects electricity market outcomes. And also identify the challenges. What kind of challenges we have in electricity markets because of renewables. I would say they are good challenges. They are the challenges that we have to solve them. And what kind of solutions we can think of. And you may realize that I don't have solution for all the challenges, not only me. Still, there are some challenges that they are open. And maybe it's a call for you to come in this area and try to resolve these challenges. Okay? But before talking about this lecture, I like to have a very quick recap of what so far we learned about electricity markets. And maybe you can help me to recap it in a big picture. So we realized that if this is time, what is the first? Of course, we have long-term markets, futures markets, and we didn't talk about that in this course. Let me get folks here. Yes, okay. Do you remember what is the first market we solve in time? We discussed that last week. Reserve markets, right? Or ancillary reserve, capacity market for reserves. And I plotted in blue because it's the TSO who solves that, who clears that market. So it's ancillary service markets. And here we trade megawatt, right? It's the capacity. Can you remember me? Can you remind me what kind of services we have that for which we have market? Can you give me some names? Yes?
Primary, secondary, or tertiary?
Yes, primary, secondary, tertiary. It's in a general terminology for these reserves. Do you remember what we specifically call them in a European market context? In abbreviations. Yes?
FCR.
FCR. So we have FCR market. We have FCR market. What else do we have? AFRR market. And what else we have? MFRR market we have. Very good. These are more in the European markets. But in Nordic area, we have a few more markets. Do you remember? Instead of FCR, we have what markets do we have?
FCRD.
Yes, we have FCRD. D stands for disturbances, and FCRN. So also in Nordic, Greek, we have these markets. Nordic area, we have markets for FCRD and FCRN. Very good. But whatever you do, it's a TSO buys megawatts from you. And by that, you are committed to provide reserve. And you will be activated in real time. Very good. I think we need a longer access. Cool. Let's say this happens D-1 around 7 a.m. Right? Okay. If you are a flexible producer, if you are a hydro plant or gas-fired power plant or whatever, or EV aggregator, for example. You can participate in these markets. What is the next market you can expect? The next decision-making time? Pardon me? Day-ahead market, exactly. It's still D-1 at noon. We have a day-ahead market. Very good. And who clears that? It's the market operator, Nord Pool or other NEMOs, nominated electricity market operators. And then we have European market clearing using Euphemia algorithm. In lecture number 3, we discussed about that. It was 3, right? Third lecture, I guess. Good. Then it's the market operators who clears the day-ahead market. Very good. So at 2 p.m., it's still D-1. Up to 2 p.m., we have day-ahead market clearing outcomes published. You can check it in different websites. Still for the next day. Very good. What is the next market that starts right away in Denmark and also in Europe? But maybe the starting time is a bit different. Do you remember? Tell me. Intraday markets. Intraday markets. It runs, if we are talking about our edge, it runs until our H-1. Again, this might be different in different countries. In Denmark, it's H-1. Right? So which intraday market we are talking about? Do you remember? We talked about 2 different types of intraday market. Yes?
It's continuous.
It's a continuous market, a continuous intraday market, which is called also in abbreviation IDC, intraday continuous. Intraday continuous. And then we discussed that there's order book. It's kind of a match of buyers and sellers. And at any point of time, you may have a trade. Right? Then we discussed that also there, oh, by the way, who is providing the platform for IDC? The same market operator. Right? It's not TSO. Then we discussed that there are also extra types of intraday markets, which have been recently added to European markets. Do you remember them? 3 auction-based intraday markets. So we discussed that there are 3 auction-based markets, IDA1, IDA2, and IDA3. We discussed about intraday market in lecture 5A. So you can watch the video again. So we saw that there is auction-based intraday market 1 to be cleared at, I'm trying to remember, 3 p.m., D-1. I hope I'm correct. Then we have IDA2 to be cleared D-1 at 10 p.m. and IDA3 to be cleared in day D, 10 a.m. So for the first 2, we clear for every hour of the next day, while for the IDA3, we clear for every hour starting from noon to midnight of the current day. And these 3 markets are exactly the same as day-ahead market. They are auction-based. You have to submit your bids or offers, and then there is a central market clearing. Is it? Yeah. Then we realized that after intraday market, who takes again the responsibility? The TSO. So whoever submitted bids here and accepted, so any generator, any flexible asset who is booked to provide flexibility services, AFRR, MFRR and AFRR, they have to submit their first activation price up to 5 p.m. D-1. For example, saying that if you activate me, my upward activation price is 10 euro per megawatt hour. But you can update it. You can update your activation price up to 25 minutes ahead of time. So you start from 5 p.m., something like here. So 5 p.m. D minus 1 is the first time that you have to submit your activation price, and you can update it by 25 minutes ahead of time. And then you can imagine that for MFRR and AFRR, TSO just checks who submitted for activation upward. So it means that, for example, generators, they have to produce more. TSO starts activating the cheapest ones until the imbalance is resolved. And the last activation price, the activation price of the last resource activated, sets the balancing price. But this is changing at the moment in Nordic and in Europe, because now we have activation for both MFRR and AFRR, so the definition of balancing price is changing to reflect energy activation of both MFRR and AFRR. But I didn't teach how it works, but it's good for you to know that. Good. And then we have imbalances, balancing market. We discussed that now in Denmark and many European countries. The balancing scheme is based on one price scheme, while it used to be two price scheme. And we discussed that under one price scheme for balancing market, there might be incentives for some producers to intentionally cause imbalance if they realize that they can earn more in the balancing market than, for example, in day-ahead or intraday market. And for that, last session, in lecture number 6, we discussed that Energinet is adding something called full cost balancing. So saying that, okay, if you cause imbalance, and if that imbalance doesn't help the system, if it's undesired imbalance, you should pay not only for energy activation, but also you should pay for the share of your imbalance, the cost of TSO to procure services to resolve your imbalance, right? Then you will be charged for energy activation and also for reservation. Good. Then we discussed that for now, everything we discussed, or in your assignment, the market unit time is 1 hour, but either all market either has been changed or are going to change to 15 minutes. So soon all market, the time granularity for all markets will be 15 minutes. So already for ancillary services and IDC, they have been changed to 15 minutes. For day-ahead market, under Euphemia, it's going to change in next June. Good. Are we missing any things we discussed? Of course, we discussed many things, but do you remember anything else we discussed? Good. So this is the overall picture of electricity markets in European context. And yeah, of course, there are more details that we discussed in the last lectures. Good. So now let's move on with the lecture of impacts of renewables on electricity markets. So here today I will try to explain you the impacts, the challenges, potential solutions, and also the initiatives that are happening in Denmark, Europe, and maybe globally. Good. So this is the numbers I got from Stine Rasmussen from Danish Energy Agency. So this shows the Danish energy sector in 1998. So based on this slide, you can see that, for example, in 1998, the 93% of supply in Denmark came from thermal power units, and only 7% from renewables. You can see the amount of CO2 produced from Danish energy sector in that year, and also you can see the energy usage, the fuels that provided energy, that supplied power plants in Denmark in that year, mostly based on coal. And this is the numbers in 2 years ago, 2023. And it has been radically changed compared to 1998, right? And now you can see that in 2023, the majority of Danish supply came from wind, 58%, on top 11% from solar. So in total, what? 69% from renewables and the rest from thermal power plants. And of course, the amount of CO2 produced reduced a lot. And also you can see the fuels for Danish energy sector in 2023. It's a radical change. And when we talk about systems with high penetration of renewables, this is an example. And the Danish target is to get 100% based renewables, right? There are a few countries with that goal, and close to that, Denmark, Ireland, and Spain, Germany, and so on. And maybe also some other countries in other parts of the group. So it's not the only ambition in Denmark to get 100% share of renewables in the power sector, but also there are other ambitions. For example, this is the ongoing Power-to-X projects to be developed in Denmark. At least this has been the plan. And based on this plan, we expect that by 2030, in 5 years, we are going to have 4 to 6 gigawatt installed electrolyzers. And what do electrolyzers do? They convert electrical power to hydrogen. And then you can use hydrogen in downstream process to produce different types of green fuels. But just to get an idea what 4 to 6 gigawatt means, the current peak demand in Denmark is around 5 gigawatt, 6 gigawatt, right? So if we really manage to get 4 to 6 gigawatt of electrolyzers, it means that just in 5 years, the power demand in Denmark will be double, right? It's very ambitious. And then you can see that how much government in total would like to support these initiatives and how much CO2 reduction it's envisioned. So when I was teaching this course 2 years ago, everyone was talking about Power-to-X. It was really a hype. As much as people today, they talk about AI. It was really hype. But today, there are a lot of ongoing discussions if all these projects are financially viable. If you talk to project developers or bank people, they use a word called bankable, whether these projects are bankable or not. Maybe you are taking a course called feasibility studies at DTU, and I think there are this kind of context. Is a project feasible, financially feasible or not? So as far as I know, the problems of the ongoing projects are not necessarily technological, it's more financial. Especially because still the investment costs are high, and also there are questions about financial risks, right? So they became like barriers for P2X projects. So whether these projects will be realized or not, I hope they will be. So it's more about the matter of time. Good. Actually, announcement that in 2 weeks that Marco will have an invited lecture. He's going to talk about financing Power-to-X projects. So you will hear more. Good. Also, have you heard about energy islands, the concept of energy islands? Is there any course that you learn about that, or you learn in your, I don't know, student jobs, or where did you learn about energy islands? Anyone like to tell me? Yeah. Yeah, for example, you said you learned, you know about it, right? So where did you learn?
I mean, I knew in the innovation course.
Okay, in innovation.
Administration.
Okay, very good. So there are two main energy islands that are being discussed in Denmark and also in neighboring countries. One of them is Baltic Energy Island. So the main idea is that the Bornholm Island of Denmark is going to be a hub for offshore wind energy. And that's what we call it, Energy Island. So there will be, hopefully, if again there will not be financial problems, not technological barriers, more financial problems, especially because of the high investment costs, then there is a potential for up to 93 gigawatt offshore wind capacity. And the idea has been, and hopefully still is, to make it done by 2030. I'm not sure that the plan is to have it all 93 gigawatt by 2030, but at least there is a potential. So you can see the website of Baltic Energy Island, and the power will be mainly transferred to Denmark, Germany, and I think also Poland. But you can see the details more in the website. The second ambitious energy island project, which has been discussed a lot, is an energy island in North Sea. And the idea is to build artificial island here in the middle of North Sea when the water is shallow, right? The sea is shallow. So you can see that back in February 2021, when I was teaching this course 4 years ago, there were a lot of news, for example, in BBC, explaining, okay, Denmark to build first energy island in North Sea. And it was a big hype. But again, last December, there were this news outside. So you can read, for example, this is the news from Danish Energy Agency back in December 2024, tender in the North Sea. The Danish Energy Agency has not received any bids. So no one submitted any bid to start building this energy island in North Sea. Or, yeah, a bit more dramatic title from Reuters, Denmark disappointed after offshore wind tenders draws no bids. So again, I don't think, I hope I'm not wrong, but I don't think the problem, the barrier is technological, more is financial. But anyway, you can see that how ambitious projects we are talking about. And all of them, they are based on renewables. So you can imagine that renewables are already impacting electricity markets a lot. And this is going to be even more in the coming years if we manage to bring energy islands or others to the picture. And of course, you can see that, I mean, if you get that amount of, massive amount of renewables, you need definitely network. You need transmission grids, and also you need power-to-X projects. Maybe to produce hydrogen on site or in the mainland. So for that, you need to transfer power to the mainland and then make it hydrogen or other green fuels. Or maybe you can do it on site. So still, what idea is more feasible financially and technologically is still under discussion. But first, we should make sure that the projects are financially feasible and people will place bid in the tenders. Good. So let's now talk a bit more about electricity markets. So that's the supply curve we already saw in this lecture several times. So let's say that the red part in the supply demand, it's renewables with a zero offer price. You already saw in the page of aggregated curves of Nord Pool or EPEX that there are many hours that many suppliers, they place a zero bid or even negative, right? Why they do negative? Because they already received tariffs outside the market. So it makes sense for them to offer negative and make sure that they will be dispatched. But if we, and then, the green one, you can say that they are conventional units, so they need to burn fuel to produce hydrogen, right? Or maybe they have other commitments, whatever. but usually they are conventional units, and usually they are they are less flexible or inflexible units. For example, they might be nuclear or they might be coal power plants. And then the orange ones are conventional units with relatively high production cost, and they are typically flexible. For example, they might be gas-fired power plants. And since gas is usually expensive, also their marginal cost, their offer price here is high. Good. So let's say that in a certain hour, this is the amount of demand we have. Of course, also we have demand curve. You already saw it in Nord Pool page. But imagine that here, the demand is fully inelastic to price. So that's why it's vertical line. So then, if it's our demand, then the market price is there. The intersection of supply and demand curves. So let's increase the share of renewables. And you can imagine what happens, and maybe you already did it in your assignments. So if we have more renewables, while having the same amount of demand, what happens is that the market price will decrease. And if even you have even more renewables, the market price will decrease further. So we see that market price is decreasing, and also importantly, we see that conventional units, especially the flexible ones, are being displaced. So a good analysis that you can do is that, if you have enough data, how often the flexible conventional units are being dispatched in the market. And by having more renewables, it will be less frequent to have them dispatched in the energy market, right? So an increasing share of renewables leads to a higher demand for balancing services. That's a side remark that you should know. Since we have more and more renewables, we need more balancing resources, right? Ancillary services. And who are going to provide those services for us? Of course, we can get it from demand side, but mostly you are going to get from these orange generators. They are flexible. So what happens, it seems that for this expensive but flexible units, their business model is changing. They used to be more energy producer. Maybe soon they will be more service provider. But what about these green generators? They are not flexible. Of course, they are relatively cheap. But imagine if we have more and more and more renewables, they are going to be kicked out from the market. There is not much business for them. Do you see that? Do you agree? Okay, while it's recording, maybe I can ask a controversial question. So these days, especially after the energy crisis, in terms of prices in 2022, some people, some parties in Denmark, they are talking about bringing nuclears. Have you heard that? Do you think with this picture it makes sense or not? The big question that we should answer is that nuclear, at the end of the day, they will be like a green generators. They are, yes, cheap, but they are not much flexible. By having more and more renewables, do we need nuclears or do we need flexible units? Right? So that's something that maybe some of us or some politicians, they are missing. Okay? Good. Any comment on that point? Let's move on. Good. This is data, I got it again from Nord Pool. You already did the same several times. For example, in December 6th of last year, in a specific time in early morning, the price in DK2 was 3.2 euro per megawatt hour. And this is the related demand and supply curve. And you can see that the intersection is here. And then the corresponding price is almost zero, 3 euro per megawatt hour. So what happens here, this is the case that when wind power is sufficient to meet entirely all demand in Denmark. Of course, here we have also import-export, but I'm talking in a general sense. So what I call it wind-driven electricity prices. When wind is enough to supply demand, of course also demand plays a role, how much demand we have in that hour, and definitely in that hour we don't have that much demand, it's 4 a.m. But you see that the price is very low because we have enough wind to cover demand in that hour. But then exactly in the same day, but afternoon, 3 p.m., the price is quite high, 116 euros. Again, why? Because the available wind power is not enough. It's far enough to supply the entire demand. And then most likely here, in this hour, you also schedule expensive generators, maybe gas-fired power plants. And that's why the price is high. But you can imagine that if we have more and more and more wind farms, the price in all hours will decrease, right? That's the main impact of renewables. Then this is another figure I got from Nord Pool. And it shows the average weekly day-ahead electricity prices in 2024. Actually, I got it in late November, so that's why December is not there. But you can also get the same picture with December included. So just as my choices, I included 3 countries or 3 bidding zones here: France, Germany, and DK2, where Copenhagen is. And then you can see the average weekly day-ahead prices. And you see that, for example, here in late November, we had the peak price in week 45. And you can imagine that maybe in this week we didn't have enough renewables to cover the demand. And it's a cold time, so the demand was high. So if you think of the share of renewables to supply demand, maybe at this point of time that share was not that high. While maybe at this point of time it was higher. But how was it so in 2024, you can see that the price was around 140 euro per megawatt in the peak time, in the peak week. But how was it in 2022? And you can see that around August 27th, the week of August 27th, the peak price in all 3 countries I picked, it was around 600 euro per megawatt hour. So 5.5 times higher than in 2024. So that's why they started talking about energy crisis in 2022. So actually just a few weeks after that peak price, there was this article from Economist saying that Europe's energy market was not built for this crisis. So the first things people started blaming was market. Market doesn't work. Since the market price was 600 euro per megawatt hour, they said market doesn't work. What do you think? Market doesn't work? Or market was reflecting the reality? Any comment? My humble comment is that market was reflecting the reality. Yes, in that period of time, for any geopolitical reasons, the gas price was very, very high. So the gas-fired power plants, they submitted a very high price, and then they were dispatched because of the demand we have in that hours, and then the market price was very high. So maybe we should think, okay, maybe the better question to answer to ask is how we can make sure that we provide more incentives for example, renewables, to make sure that investors, they're going to invest them in the long term. Maybe this is a good question. So that's why also this electricity market reform of EU came up, actually in 2022, discussing that, okay, we have to think about incentives. What kind of incentives we are preparing, especially for renewables, to make sure that in long term, there will be more incentives for investors to invest in these projects. But actually, this is not what we are seeing. I just told you that back in December last year, there was no bid in the tender for offshore energy hub in North Sea. So still it seems that the renewable projects in large scale, they are not very attractive financially. So this is, I think, what we should work on. And if you like to stay in academia or in companies, but trying to find solutions, this is the challenge that you should find a solution. Okay? Have to make sure that there are enough incentives for renewables in long term. Otherwise, in short term, I'm not sure that electricity markets are really not working. For example, in those times, they started thinking, okay, let's put a cap on the price offer price of different peoples. I don't know, saying that you are not allowed to place a bid more than X euro per megawatt hour. Is it really a solution? I'm not sure. Okay, is everything clear? Good. What challenges else do weather-dependent renewables pose? Okay, we discussed about price. Then you see that how sensitive the topic is. People really react immediately saying that the market doesn't work, right? Okay, fine. But what other challenges we have because of renewables? So you can think of supply variability, so fluctuations across time, ranging from seconds to hours, and supply uncertainty. It means that we can't 100% predict how much renewable energy production they're going to have, and also other challenges I'm going to talk about. In this slide, what I like to really emphasize is that uncertainty and variability, they are two different things. Right? So sometimes, many times I see that people, they confuse and use them interchangeably, but they are not. When we say that renewable power plant, the renewable energy is variable, we are not talking about stochasticity. We are just saying that over time, the wind energy in terms of megawatt hour, it might be something like this. Over time, there is a variable production. But the stochasticity means that it's hard, it's challenging to forecast it beforehand. And if you want to forecast it well in advance, it becomes even harder. So it means that if you like to forecast for the next day or for the next week, it's something like this, or even bigger uncertainty. It means that any production here, this range shows a distribution of potential production. For example, if you bring it, it might be a distribution something like this. It means that most likely the production will be this. It's a distribution function, right? But any production in this range might be possible. And here I put a low range. Sometimes it's very uncertain how wind power production will be, or solar. So I hope it's clear for you that how variability and uncertainty or stochasticity are different. Clear? Good, yeah.
Wouldn't you argue there's some sort of relation between the two?
How?
I mean, a higher variability maybe will give you a higher uncertainty the more the longer.
Yeah, there might be conditionality. What we're talking about is conditionality, and that's a good question. It means that depending how much in expectation you may produce, it may affect how much uncertainty you may have. Yes, there are definitely some correlations, and we call it conditionality. That's very good. Did I answer your question? Now let's talk about challenges in terms of renewable generation variability. So how many of you have seen this curve before? A few, not many. Okay, it's a very famous figure, so it's good to make sure that you know what it is. It's a daily profile of net load. What is net load? Net load is load, demand, minus renewable generation. It simply means that the demand that should be supplied by non-renewables, by conventional generators. And this curve comes from California ISO, CAISO. And you can expect that something similar has been happening also in other parts of the world. But what is that? So as I said, this shows the net load, demand minus renewables, the part of demand that should be supplied by conventional generators, over a typical day. And the y-axis is the net load in megawatts. So what's happening is as following. By the way, the curve is commonly referred to as duck curve. And can you spot the shape of the duck? Do you see a duck here? It's a duck, right? It's called as duck curve. So this is the story. So around 7 to 8 a.m., there are many solar panels, especially rooftop solar panels in California, distributed across the state with significant aggregated capacity. And at 7, 8 a.m., these panels start injecting power into the grid. So that what happens then, the net load curve declines because most of the demand now can be supplied by solar power. So the net load starts declining. Is it clear? And then around noon or 1 p.m., we have the maximum solar power injection. And therefore, we have kind of minimum net load of the day because the most of the load in the grid are being supplied by renewables. So there is only a small part of the load that need to be supplied by conventional generators. Is it clear? And what happens? Okay, yeah. And the interesting thing is that the lower curve leading to a fatter dog, it was initially expected to be realized in 2020, but already it observed in May 2016. So this fat dog already realized way before than the initial guess. Then the most interesting thing is this. Around 6 to 9 p.m., a solar power injection decreases, and power demand from conventional generators increases. What I say is that the net load rises sharply. What does it mean? It means that, for example, in the time period of 6 p.m. to 9 p.m., the increase is 13 gigawatt. So in 3 hours, if you are the system operator in California, based on this curve, and maybe now it's even worse, based on this curve, you should be able to increase the production of conventional generators, the thermal generators, in 3 hours in total by 13,000 megawatt. Do we have a problem in the capacity of generators in California? No, there are sufficient capacity. But the problem is this ramp. The conventional generators usually are not that fast to be able to increase their production in a limited time of 3 hours by 13 gigawatt in 3 hours. Do you see the problem? So as I said, the concern here is not the lack of generation capacity, but insufficient ramping capability of conventional generators. That's a challenge. So when you hear that, we see a phenomena, something like duck curves, the problem is the ramping, right? Ramping capability. That's one challenge coming from variability. It's not about the stochasticity. This is another example I got from Finland. So if you go Fingrid website, which is the Finnish TSO, they also provide a lot of good data. So for example, in the first week of December 2024, I got this data from Fingrid. And you can see that this is the total wind power generation in Finland, the first week of December 2024. And in the period of 13 hours, only 13 hours, the total wind production increased from 500 megawatt to something around, around 6,000 megawatt in only 13 hours. So the difference is 5,675 megawatt in just 13 hours. So you can imagine that it's like a big generator that fluctuates a lot. Just to know that, okay, how big this value is, it's equivalent to 1.7 times of the capacity of the Finnish largest nuclear power plant. So in 13 hours, the wind capacity, the realization of wind production has been changed by 1.7 times of the capacity of the largest Finnish nuclear power plant. It's a lot. Or this is another example from Belgium, and I got this data from Elia. Also, Elia provides a lot of good information and visualizations in their website. So this is February 2021. I kept this figure from 4 years ago when I was also teaching this course. And you'll see that in that specific month, the minimum of wind power production, the total wind power production in Belgium was 40 megawatt, and the maximum was 2,159. So a lot of change, a huge change in wind power production. So you have to be ready for that. Good. So variability is one problem in terms of how much wind you may have. And also we saw that we have ramping problems in the case of duck curves. Now let's talk about renewable generation uncertainty. Again, another real-world example. This is again from Belgium. And this is for the last November 18 and 19 from the last year. So the gray one shows the forecast. They had forecast of total wind production. And the orange one here is the actual realization. And you can go Elia website and see it for every day, even for today. And here I saw that for this specific days, the difference of wind forecast and realization. So here we are talking about uncertainty, stochasticity, or wind forecast error. The wind forecast error at this point of time is 1,134 megawatt. Is it big? I went and checked what was the total load in Belgium in that hour, and I realized this forecast error was amount to 14% of total Belgian power demand in that hour. It means that your forecast error simply is 14% of your demand. It's a lot. So when you have huge amount of renewables, you should think of ways to solve challenges coming from variability and also uncertainty. Can you think of other challenges? The lecture is about impacts of renewables on electricity markets, right? What challenges else do we have? This is a figure from Eneginet. And Eginet published a report on their outlook of ancillary services in 2040. So more renewables, stochastic renewables, means that we also need more balancing resources, more FCR, more MFRR, more AFRR capacity to buy. And here, for example, you see that this is how an Eginet projects their need for FCR services in DK1. So actually, they released this last year, so it was something like here. Now, the need is here. But you can see that in 2040, they have different projections of lower increase of the need or higher increase of the need. So the real FCR need in 2040 will be something here. Or maybe also we have forecast error here, who knows. But you see that how drastically the need for balancing resources is increasing because of renewables. Okay? And actually, this is very important for TSOs to release these projections. But how accurate it is, it's a different story. Because we talked about how financially challenging it is to provide the finance for new projects. So more revenue streams you have for your projects, it's more likely that you manage to build that asset. For example, if you are thinking of Power-to-X assets, of course your main business will be selling hydrogen, but also there might be a byproduct of selling ancillary services. But then it's important for you that, okay, how big the market for balancing resources will be in 10 years or in 15 years. And that projection helps you to decide. So how much the need will be, that's one thing. But what the price will be in 10 years, that's another thing, right? And you see that how complicated these projections and these investment decisions can be. Good. And then we saw that by increasing more and more renewables, we are pushing out the conventional generators. Of course, still we say that they will be there for providing ancillary services, but maybe it's not enough to keep them. Maybe some of them will be phased out. So it means that in future, it's a likely scenario that we need more balancing resources while we have less conventional generators. Then the question is that, who is going to provide us balancing resources? And then most likely we are thinking of course, hopefully we will manage to have more storage in the system, more Power-to-X units, electrolyzers, also maybe more assets from the demand side, hopefully providing balancing resources to the system. When I say balancing resources, I'm talking about different types of ancillary services, right? So what are the examples of this demand-side resources, like electric vehicles, like heat pumps, like boilers? But at the end of the day, the main primary job is not to provide services to the grid. People, they use electric vehicle for transportation, not to provide services to the grid, right? So then there will be a baseline, how much demand an aggregation of EVs may have, and then based on that, maybe we can provide balancing resources. That's why now we have new players called aggregators, flexibility aggregators, who try to pull different demand-side assets, put them together, and provide balancing resources. But that baseline is stochastic. You don't, for example, imagine you control thousands of EVs in your portfolio, and you can provide FCR services. But how much FCR you can produce depends how much these 1,000 EVs will consume every 15 minutes of the day after. Do you know it a day before? No. Is it easy to forecast? Not necessarily. When do you need to submit your bid for FCR services? A day before. A lot of stochasticity. Um, Good. The other problem that renewables pose is grid problems. It's not directly a problem from renewables, but to be able to transport renewable energy, you need grid. Well, first think of big projects like energy islands, either in Baltic or in North Sea. Okay, if you manage to produce a lot of wind power in the middle of the sea, you need a way to transport them to the mainland. So building new transmission lines itself, it's a big project, both technologically and also, most importantly, financially. But also think that we want to add a lot of renewables. Maybe imagine that in our neighborhood, all of us, we start installing rooftop solar panel in our houses. Is the distribution grid in our neighbor ready for that? So this slide shows the grid congestion status in the Netherlands. And I think our Dutch colleagues, they are very good in visualizations of their grid problems. So here you see that red means that very congested. How for the power injection and for power injection and power withdrawal, how congested the system is. In the transmission level and also in the regional level, in the distribution level. And already you see that, how congested the system is. And actually you can go to this website and play and see how the status is at the moment. I can give you, for example, in Australia, one of our colleagues was explaining that there are a lot of rooftop solar, and at some point of time, there's a lot of injections from this rooftop solars to the grid, and then the grid has technical problems, for example, voltage issues. Then there is no way other than curtailing this renewables. Though you want to absorb renewables, but you can't absorb it because of the grid problems. And then we have a lot of renewable curtailments there, which is not really nice, right? We want to have more renewables to be able to use that. So this grid connection and network capacity also is one of the challenges that we have to see when we talk about renewables. And of course, this is the grid has also a clear impact to electricity markets in terms of prices, right? Good. Are you following so far? The last problem I like to mention is, it's not really in my area, but I think it's good to mention it. It's about the lack of inertia, the non-synchronicity. Grid connections for renewable resources often rely on power electronics, right? Inverter-based technologies. So when you have more and more supply from inverter-based resources, that reduces the available kinetic energy you have in the system. You have less inertia in the system. When you have more inertia system using these rotating generators, it's easier for you to keep the stability of the system. But when you have less inertia in the system, kinetic energy in the system, then it's harder to keep the stability of the system. Well, for example, that's a figure I got from this ENZOE report, European Network Transmission System Operator. It shows the effect of amount of kinetic energy on the behavior of frequency after a loss of production with and without FCR. So let's say that we have FCR services. We activate FCR, but how is the profile of getting frequency back to the nominal of 50 hertz? So you can see that how fluctuating is when we have less kinetic energy in the system, less inertia in the system, right? So having low inertia systems because of more and more renewables is a problem. But again, it's out of my expertise. But our colleagues, especially in the control theory and also fundamental power system colleagues, they are working something called grid forming technologies, still based on power electronics, to help improving inertia of the system. Okay? So you can see that adding more and more renewables pose a lot of problems in terms of variability, uncertainty, market problems, grid connection problems, and also stability problems. And we should be able to find solutions for all of them. If we don't do that, if we don't find solution for all of them, then it becomes a barrier for more integration of renewables. Good. Yes?
Seems like all these problems caused by more renewables was very predictable even like 10 or 15 years ago. So why, is there some reason to why there's such an increase in the penetration of renewable energies but not such the equivalent effort in adjusting the grid and all that?
No, there have been always efforts, but the problem is that efforts also, it should be at the same size, scale of the amount of renewables we are adding.
So why is it not the same scale?
There are. Yeah. For example, this grid forming solutions. There are good solutions. Okay, what I'm saying is also a personal opinion. I think for all the solutions, for most of them, we have good technological answers. The main barrier, again, this is not the example, is the financial problems, I would say. So that's why learning about energy economics, markets, it helps, right? So for most of the challenges, I think we have technological answers, not financial answers. Did I answer your question? Good. I like to share some solutions for you, but I'm not saying that these are the old solutions. Still, some of the challenges are, they have open questions. There are open questions how to resolve them. But here mostly I focus on challenges related to variability and uncertainty of renewables. So let's get back to market context. I think for our solutions, we can think of different for our challenges, we can think of different solutions. In terms of defining maybe new market actors, new players, I'll give examples. Maybe we can think of exploring new resources for balancing, if the problem is the balancing resources. Maybe we can think of new products. For example, FCR is a market product. I don't know, intraday trading, intraday bids at the end of the day is a type of the market, and the bid is type of the market product. Maybe a bit more radical thinking. Maybe we can think of revisiting current market designs. And of course, when we're talking about revisiting, you can think of very radical changes. Maybe you can argue that in 10 years, the way we clear markets today is based on what I explained to you. Maybe it doesn't make sense at all, right? So these are open questions, actually. So let me give you a few examples. For example, when I say new products, what kind of products I'm talking about? You saw a duck curve in California, right? So Kaizo then started thinking, oh my God, I have to do something. I have to do something, right? So in the duck curve, you saw that the change is something like this. This is the net load change. So in the matter of 3 hours, there is a need of 13 gigawatt increase in supply in 3 hours. And as I said, the problem is the lack of ramping capability, not the lack of capacity of generation. Maybe our generation capacity, they can handle this ramping in 6 hours, not in 3 hours. So because of this problem in California and later in MISO, Mid-Continent Independent System Operator, so in the Midwest, they started adding a new market product called FlexiRamp, standing for Flexible Ramp Product. Have you heard of it? So that's a new product to be able to solve the problem. One way of thinking is that, okay, we have ramping problems. Do we have enough capacity in generation? Let's go and invest in more very fast responding generators. That's one way of thinking, but very costly. The other way is thinking a bit more market-based, market-oriented way. So here they define this product. What it shows that, for example, they say that based on the net load forecast, the system operator, for example, Kaizo, reserves a certain amount of flexi ramps at hour 3. So you see that at hour 3, we can have a forecast how much the increase of net load will be. You can have different scenarios. And then you reserve some fast generators for providing ramp in certain hours. So for example, if you have a very fast responding generator with a capacity of 100 megawatt, you can say that, okay, I pay for you, don't dispatch at full capacity of 100 megawatt. Let's, for example, dispatch you 50 megawatt and leave 50 megawatt of you for increased change in production in 2 hours. Is it ancillary services? No. It's a ramping service. Are you following me? And of course, here there is opportunity cost because we are asking this generator to not be fully dispatched in the day-ahead market, for example. We keep them ready for sharp increase when we have problems. So of course, for this flexi ramp, we have to pay that generator. So in US and California, there is a market for flexi ramp. There is a price for flexi ramp. And then generators, they bid based on their opportunity cost. Is it clear? So in my opinion, this is a very innovative solution, market-based solution. It's a new market product. So when you have a problem, you can think, is it possible to define a new market product? Say, or I don't think there is a product for that, but these days there are sometimes in different parts of the world, there are extreme events, right? Hurricanes or something, or earthquakes or whatever. Is it likely to see this kind of events? No. There are extreme events. But to keep the system resilient, it means that in very extreme cases, the system will be okay. We need some generators, some assets to provide reserve. I don't know if you call it reserve or not in those situations. By reserve, I'm not talking about ancillary service anymore. I'm talking about being reserved for extreme situations. Do we have a market do we have any market product to offer this kind of service? No. Is it time to think of this kind of products? Maybe. Right? Good. Yeah, if you want to read more about FlexiRamp, just Google it. You will find a lot of nice reports. But one of them that I found good is this Kaiser report. New resources of flexibility. So, as I showed you, for example, for FCR, we imagine we will need more and more FCR services in the next 15 years, and the same story for other ancillary services. And also I told you that the conventional generators are being phased out, so we need new resources who can provide us flexibility. And also I told you that one of the resources are demand-side flexible resources. So you can think of different aggregators. And these days there are also many aggregators in Denmark trying to pool demand-side stochastic assets, electric vehicles, heat pumps, boilers, blah, blah, and bid in the market. Or water pumps. You can, if you want me to name a few companies, I don't know, you can think of IBM, for example. They are active in Denmark to design something called Flex Platform. That pool different assets and then offer different asset service models. Or different companies like, I don't know, Neogrid or WAS or Philip and vice versa. And mathematically, also their problem is very interesting because they have to pool different assets, manage uncertainty, make decision-making under uncertainty, and bid in the different markets while forecasting what their price will be. Very interesting decision-making problem. While fulfilling the physical constraints. One important thing that maybe I mentioned, I told you in maybe lecture 2, is that most of these resources, they are located in the distribution grid. For example, electric vehicles or heat pumps. And if you would like to provide ancillary services like FCR, MFRR, it's a services for the transmission system operator, for the TSO. So what happens is that if we have frequency problems or whatever, or imbalance problems, the TSO will activate these local resources in the distribution grid, right? So maybe the TSO's problem is solved, TSO is happy, but maybe activating them will cause local problems to the TSO. So TSO is happy, but TSO is unhappy. What happened? So here, that's why TSO-DSO coordination is very important, is essential. So to be able to fully leverage the flexibility of demand-side resources, we need to make sure that TSO and DSOs, they are coordinated. For example, one easy way, easy, maybe it's not the right word, is that maybe to be able to go and bid in FCR market, you should be able to get eligibility qualification, green light from the DSO. You say that, okay, I want to bid maximum X megawatt in FCR market, then first DSO should check it. If that happens, will there be any local problems or not? If not, DSO says, fine, green, go, and then you go and participate in the TSO. That would be one way. Yes?
I'm just thinking that the flexible aggregator may have maybe EVs in the whole DK2, for example, right? So maybe different DSOs. So they need a huge cooperation between.
Exactly. It's a very good point. We are not talking about one DSO. Maybe we are talking about multiple DSOs. Maybe your assets are spread geographically in the domain of not one DSO, but multiple DSOs. But the problem is, it's a very big challenge, right? And still, I'm not sure that there are very effective solutions for DSO coordination placed. Still more efforts are needed. Maybe you can help. Another resource of flexibility is multi-carrier energy systems, right? For example, there are assets in the intersection of power system and other assets. For example, heat system. Think of heat pumps, for example. Or natural gas, gas-fired power plants. They are flexible, but also they are connected to gas network. They are gas demands, right? Or maybe you can get flexibility from water system by tuning the power consumption of water pumps, right, in the water system. So, for example, you can think of combined heat and power units, CHPs. You have one in DTU campus, right? A small one, CHP. So CHP can produce power and heat at the same time. But you can play with that. How much power, how much heat to produce, and at different operating points, there is different efficiencies. Right? So this means that whenever in the power system you need flexibility, maybe you can play with the CHP schedule, with the CHP set point, and then get flexibility with that. But what is the cost, or what is the problem? By doing that, you are also changing the heat production of the CHP. So maybe by that, you are propagating your uncertainty from power system to heat system. You're just propagating your problem to the different sector. So before that, before doing that, you have to make sure that heat sector is ready for that. Are you seeing the problem? So what I'm talking is about a systemic risk. We have to, so people, they think that, okay, if we integrate more and more sectors together, it's good. The system becomes more resilient. We can get flexibility from heat system, from gas system. So in the power system, if we have problems because of renewables, we get flexibility. But what we don't sometimes see is that we are pushing, we are propagating our uncertainty from power system to heat system, to gas system, to water system. It is fine as long as they are ready. It doesn't cause problems in other sectors. Otherwise, we may have just propagating of the problems from one sector to another. Is it clear? And in a worst case, worst case, what will happen is cascading failure. The power system is failed, now we push failure to heat system will fail. So that's why, again, to fully exploit this flexibility, proper coordination between power system operator and heat system operator is essential. Or you can think of the same for gas power plants. So gas units, gas-fired power plants, they can provide us flexibility. So it means that when we see fluctuations in the power system, we can ask gas power plant to kill the imbalances, right? But this means that the gas demand is also fluctuating. So then maybe we are going to have problems in the gas network. But there is one extra degree of flexibility in the gas network, also the same in the heat sector, I forgot to mention. And it's the stored gas or stored heat in the pipeline. And we call it stored gas in pipeline, we refer to it as line pack. Right? So maybe, as I said, the gas demand is changing because of the variant gas consumption of gas-fired power plant. But maybe having line pack, stored gas in the line in the pipelines, help us to keep the gas network balanced and working healthy. So to be able to use this flexibility of line pack, again, it's essential to have a proper coordination between power system operator and gas system operator. Is it clear? Who is the gas system operator in Denmark? You don't know? Energinet. Energinet is also a gas system operator in Denmark. Also, you can think of electrolyzers, power-to-X assets. Also, electrolyzers are consuming power to produce hydrogen. Are electrolyzers flexible? Yes. But you should be careful of the degradation. But the problem is that most of the times, electrolyzers may have a constant contract with hydrogen off-takers. So maybe you are not very flexible to play with the consumption of the electrolyzer because more variability electrolyzer consumption has, it means that more variability you have in hydrogen production. Of course, you can say that I can have a hydrogen storage, but it's very expensive and hard to have it, right? Good. So, new resources of flexibility, we discussed. Now I'd like to talk about new types of market players. I already discussed about flexibility aggregators, and I already gave you an example of IBM. Actually, this is the picture I got from IBM in Copenhagen. So you can see that what is the IBM's estimation of getting flexibility from different demand-side assets. So I had industrial PhD with them. He graduated. So his job was exactly to see that, okay, how we can pool different type of flexibilities from different assets, bring them to Flex platform, and then to bid in different markets. So what we did, or you can think of, for example, a pool of 1,000 EVs. We did that. Also, you can think of one big plant, industrial plants, for example, as a big demand consumer. So we checked a plant in Jutland for steel and also for a galvanizing process. It's a big thermal plant. And then you see that, okay, how much flexibility you can get from that plant for electricity consumption. Okay? So they have a furnace, and then you see that, okay, how much flexibility you have for that plant, and you can play with the consumption of that plant to produce different types of, for example, ancillary services. The last things I like to tell you, but maybe it's a bit radical change, but maybe in 10 years or 20 years, sooner or later, it's essential to think in that direction. And it is revisiting current market designs. What I told you. So in 20 years, 10 years, if we have like 100% renewable share, does it really make sense to keep this order or not? If you want to change it, it will be a radical change. It will be hard to convince, in practice, these things to change. But if you do that, there will be a big impact, right? Rather than trying to solve small things, maybe you can solve a big things at once. So exactly, this is what we discussed. This is what I tried to also plot it here. But maybe it's time to rethink electricity market design. Let me give you an example. Renewables, we know that they are stochastic. But they are bidding deterministically. They bid in day-ahead market like 10 megawatt at the price of 0. So why not to let renewables bid stochastically? For example, to bid a distribution. It's a crazy idea, right? Is it good, or does it bring more problems? I don't know. Right? Or you may think even more radically, say that, okay, I don't need these things. I only need maybe a real-time market. I'll talk about that even a bit more. So the market, whatever design you think, the market should align with the system's underlying physics. At the end of the day, you are transferring power from one point to another. It should fulfill Ohm's law and Kirchhoff's laws. We know that. So whatever you think as a design, it should support a high share of renewables, even 100%. And also it should be able to get flexibility or services from flexible but stochastic resources, like aggregation of EVs, aggregation of heat pumps, and so forth. So think of what kind of designs might be possible, but whatever it is, it should reflect these things. Alignment with physics of the system, supporting high renewables, and supporting stochasticity of renewables and flexible resources. But whatever design you think, there are some certain things that you should check them. And the most important thing is efficiency, right? We discussed about that. Your market design should promote maximum social welfare. If your market design, whatever it is, it doesn't bring maximum social welfare or it's not aligned with maximum social welfare, if it's not aligned with Nash equilibrium, it means that no one wants to deviate, then maybe it's not a good design. Incentive compatibility, it means that the market should incentivize you or market players to bid trustfully, to truly reflect the operational cost in their bids, not more than that. So whatever design you think, it should be able to guarantee cost recovery. It means that your profit will be minimum zero, but not negative, right? If you participate in a market that you may earn not only nothing, but you may lose, you will rethink, really, I want to go in that market? So you need to provide a certain level of assurance to market players to enter to that market. Revenue adequacy, as a market operator, you don't want to be in a position that you have to put money from your pocket, right? Transparency, it's important. Always players ask you, why the price is this? Why the market clearing outcome is this? And you should be able to explain that. So I just mentioned you an example of probabilistic bidding. Is it aligned with transparency? No, I'm not sure. It will make understanding the market outcomes harder. It will not make it easier. So transparency is also a key factor. A very key factor is right investment signals. So that's why, for example, we have this capacity market, right, that we didn't cover in this course. So whatever the market design you think, hopefully if it will provide incentives for investors to further invest in different technologies, including renewables, storage, etc. And now also people, they are thinking of new values, new metrics like fairness. And what fairness is, you can search yourself. But what I'm saying is that we are not sure that all these good things can happen at the same time. Sometimes you need a trade-off. So when you propose a new market design, you have to see which of them you guarantee by design and which of them you are losing. And if you are losing, what is the magnitude of your failure? Right? So market design is a big topic, and I'm not sure we are yet there to say, we found a way, a new market design to stop this and doing it in a new way, right? But at some point, maybe we have to. Maybe you remember this slide I had in lecture 3, I guess. If one day we get a point that we have 100% renewables in the power system, with maybe a good penetration of also storage, then operational cost, the marginal cost of the system will be zero at the operational level. I'm not talking about investment cost. So then whenever you clear the market, the price is zero or almost zero. Maybe then you can think electricity market should be just a service market, similar to market for in the communication sectors. Maybe. Is that a good idea? I don't know. But it's just a hypothesis. Good. That's the last slide of mine. If you want to read more about future electricity markets, different hypotheses. I'm not sure that there is a certain way of thinking of future market clearing, of future market designs. But there are, among many, many good papers, I picked 7. So papers by Paul Josko, Bill Hogan, David Newberry, Ben Hobbs, Shmuel Loren, Pierre Pinson, Josh Taylor et al., and Yunong. Most of them, they are very big names. They are influential researchers in the context of electricity market and market design. So if you like to read more about these challenges and potential ways, maybe these are good papers that you can check. Yeah, that's all. And as I told you today, there is no Kahoot because it was not easy for me to design Kahoot quiz based on this lecture. Yeah. So this is the end of lectures on system and market side. And from next lecture in 2 weeks, we are going to start talking about problems from a stakeholders' perspective, in particular from wind farms' perspective, and how they can optimally bid in different markets. And you will see that we are going to talk about decision-making under uncertainty. Thank you.